So those first two structures done in what I think will probably end up being the first movie of this work through. I went through quite a lot of detail. From now on, I'm not going to go through so much detail, but I'm perfectly willing to expand upon answers via email if anybody has any questions. So next one, PF3, common sense, phosphorus 3 bonds, 1 lone pair, fluorine 1 bond, 3 lone pairs. Common sense just means wanting to get up to the octet rule. And so phosphorus goes in the middle, as it is the less electronegative, but also the one that wants the 3 bonds. Fluorine's terminal atoms, as they only want 1 bond each. Count round the phosphorus, which is the central atom, 4 groups of electrons. 4 groups of electrons get away from each other as much as possible by forming a tetrahedral geometry. In this case, 3 of the bonds, 1 lone pair, and so we don't see one of the arms of the tetrahedron, so we see a so-called trigonal pyramidal one. So there we are, was a tetrahedron, but we replaced one of the arms by this lone pair. Angles in a tetrahedron, 109.5. Lone pair distorts it, so a little bit less than 109.5. And again, anytime you have polar bonds, which we definitely have with fluorine involved, bonding to the phosphorus, and a lone pair that distorts the structure, unless the lone pairs cancel each other out, which is an extremely rare phenomenon, it will be a polar molecule. C2H6, common sense. Ethane, should know how to do that straight off anyway. Here we got 2 carbons as the central atom, but they're identical carbons. They both have 4 groups of electrons, which again makes them tetrahedral. In all cases, those bonds are, or those electron groups are bonding groups, so every atom, both the 2 carbons, are indeed tetrahedral. Angles of 109.5 as far as one can predict. There'd probably be a little bit less because, of course, carbon bigger than hydrogen and so forth, but 105 is what you say, and it's a perfectly symmetrical molecule, cancels out everything, so it is non-polar. SeO3, no common sense, because again, all of these have 6 valence electrons, so want 2 bonds. Only way you can make 4 atoms in a molecule, give them 2 bonds each, is to make a square. You only see squares when you're in carbon chemistry. So 24 valence electrons is our target. Selenium less than oxygen. There's the trial structure, all with single bonds and enough extra dots drawn as lone pairs around each atom to take them up to 8. 26 dots, don't like that. So we have to turn 2 of the lone pair dots on 2 bonded atoms into a double bond like this. Again, I could have picked the left oxygen, the right oxygen, or the down oxygen because of that resonance topic, again discussed in an extension video in Molecular Structure 1. Each of these selenium-oxygen bonds is equivalent. So anyway, the selenium's the interesting atom. How many groups of electrons around it? Double bond is 1 group, single bond 1 group, single bond 1 group. 3 groups of electrons. 3 groups of electrons arrange themselves trigonal planar. We've already seen that in the SO or SeO2 structure. 3 bonds, no lone pairs in this case, so we see all of the trigonal planar. Because all of them are equivalent, the angles are exactly 120, and when you have a nice, beautifully symmetrical structure like that, if we go through the questions, yes, there's polar bonds, there's no lone pair on the selenium, and everything the selenium's bonded to is the same, they're all oxygens, so it is a non-polar molecule. C2H4, harking back to the previous slide with C2H6, common sense molecule, ethene, double bond between the 2 carbons. Each carbon is a central atom, each carbon has 3 groups of electrons, so it will be trigonal planar. All 3 groups are bonding groups, so thus we will see all 3 of them, so the shape will be trigonal planar, angle of 120, except here, of course, we've got a double bond in one of the positions and single bonds in the other, and double bonds are significantly more repulsive than single bonds. So what will happen is that this double bond will push those hydrogen bonds a little bit away from itself, which means that the angles involving the carbon-carbon double bond will be a little bit greater than 120, and thus the angle here, the hydrogen-carbon-hydrogen angle that's being pushed away by those lone pairs, by the electrons in the double bond, will be a little bit less than 120. Regardless, it's a nice symmetric hydrocarbon. Hydrocarbons are non-polar, at least at this level of understanding.